Hello, we're back and we're off mute on time for once. So, we've been doing a lot of horizontal landings on Luna lately, and we tried out this airbag idea, but we didn't. We had a glitch in the data logging, so we couldn't see the data log. Kind of annoying. And what we want to see the data log for is to find out how hard we're actually hitting the surface when we finally land, and give us an idea of whether or not these would be a successful form of landing gear and final touchdown. So we finally got all the data collection worked out. And so let's just jump right into it. We'll do the first flight here with our airbags, this time with the data, and we'll see how she goes. Let's just head on out. And while that's going, I'll get the data log hooked up here. Actually, I have to wait for the new file. There we go. All right. Come back to our normal view. You see everything stabilizing. We started off kind of wobbly. So we're going to fix our altitude, lock our vertical heading, and we're not going to go out quite so far so that the flight's not so long. So we're only going to go up to an altitude of 5,000, and we're going to head in a slightly different direction. We're basically going to go due west, and we want to split the difference, and we'll just go down to 45 instead of 35, and this will be a not quite such a shallow takeoff, and we won't have such a shallow landing, and it'll just be a little bit more gentle in overall. Obviously, we're not going to get to the same place. We're going to stay pretty much up on this plateau, just about 26 kilometers that way. So 3, 2, 1, here we go.
All right.
And we're off, and all the charts jump up in size.
I'm interested in the data.
There we go. So luckily this will be pretty short flight, but we'll probably speed it up even more here. That apparently did not work. There we go. We don't really need to time warp because we're going to just stay up on this ridge. We're going to land over around about in this area, I believe it is. See which
That's
way.
a pretty shallow crater.
Yeah, I'm not particularly targeting the crater at this point because really the goal of today is to flop over and measure how much force, or in this case, how many meters per second was our last sample before it went to zero.
Yes.
And since each sample is a tenth of a second apart, we can use that to calculate the g-force.
Yes.
And of course, this will be based off of g's on Earth, because all of the equipment that we're sending will be measured and tested on Earth before it goes, and so it'll probably be rated in Earthen g-forces as to its maximum shock that it can handle. But I like the idea of just landing in the
everywhere,
just above the crater, and letting the crater collect all that extra regolith. So in this case, it looks like we're going to go right in here to this little ridge. And then since we've got pretty decent altitude all around, and it's not all that,
looks pretty sloped.
It's kind of sloped, but it's not too horrendous. You can tell by the actual data here. Although
Yes.
it's not very zoomed in, so it's a little hard to tell. But you'll also notice all this instability in our thrust. It's because we're trying to stay above ground level, and the ground level is constantly changing. If we switch modes to where we're staying at altitude above sea level, what it does is it takes whatever it takes whatever altitude we're currently at and changes from following ground to following the sea level. And in doing that, you can see how much calmer our thrust gets over time. So let's see.
So
That's a
do they
decent.
call it sea level on any other planet?
Well,
What do they call it?
they in the game they call it ASL, or I guess average sea level. And on most planets with fluid, you'd have a sea level. Um, Assuming all of the seas are interconnected. That's why all of ours are at the same level, is because they're all interconnected. Of course, if they weren't interconnected, they wouldn't be seas; they'd be lakes. Uh, Very large
What
lakes.
about the planets that are their seas are deep inside?
Oh, sea level is negative beneath the surface, huh? I don't know. They'll figure out some standardization for that, I'm sure, once they get the
I'm sure
lunar
there is.
GPS going. Which, by the way, there is a program for lunar GPS in the works, not surprisingly. So let's get our lateral speed all zeroed out. I'm still doing it with our little tilty method, which has its odd side effects. But there we go. That's only 3. All right. Now we're going to, in this case, the airbag version, we're going to drop down to a height what was originally or previously called pad printing height, where we were printing the landing pad. But with the airbags, we don't necessarily need such a hard surface to land on, and the airbag itself can deform and land over rock and still be okay, that kind of thing. Of course, all these airbags would be made out of some sort of super tough Kevlar-like material, I'm sure. All right, that's now we've got a little bit of let's
It's a lot of
zero
tallow.
out this. Oh, plop. Didn't get a chance. So one of the downsides to this algorithm is if you're on a hillside, then you can get some instabilities because the ground is
But
changing out
it
from under
proves
you.
my theory that it works.
Well, it proves that you can flop over like that. So now let's take a look. Well, first off,
Oh yeah, you don't know if anything survives.
let's go take a look here at the data. Here's our vertical speed. So if we just zoom in on our vertical speed, you'll
So if
see.
you're carrying something, it may not have survived it.
Well, we had a vertical speed of about negative. The worst vertical speed we had here. This is where we turned off and kicked over. This was our vertical speed at negative 7.5. Maybe call it 8. So roughly negative 8 or
It
so
only goes to 10.
meters per second. Yeah, well, here's negative 7.5. Are you seeing my cursor, by the way?
Yes.
Okay. You're seeing the cursor over the graph?
It's a
All
little.
right. The plus sign?
Yeah.
All right. So maybe it's 8-ish. So we hit about a negative 8.
It only goes to 10.
Right.
That's harsh.
What do you mean it's harsh?
That would be a hard thump.
Well, that was my question. How do I know what a hard thump would be? And so we have to convert negative 7.5, negative 8 meters per second. And since our samples are 1/10 of a second apart, we went from negative 8 meters per second to 0 in 1/10 of a second. So we want to take a look over at this, and actually, let's go do our calculation here. So our start speed was roughly negative 8, and it went to 0 in 1/10 of a second, and that equals, not surprisingly, roughly 8 Gs. And the reason that is because 1 G is 9.8 meters per second squared on Earth. It's 1.6 on Luna and the Moon. So because it's 9.8 and it's 1/10 of a second, it roughly works out to meters per second equals Gs. Close. So roughly 8 Gs was our landing. And you say, well, is that a lot? Right? Is that too much? And I was like, well, I don't know if that's too much. Let's see. So I was like, okay, they have these Shockwatch stickers. These are things that you would put on your package to make sure that it wasn't mishandled in shipping. And they have some basic ones. 15G forces if you're sending a generator. If you're sending cabinets and refrigerators, they can handle up to 25G electronic equipment, I guess. I don't know why that's so robust relative to everything else. You tend to think of electronics as being less robust in a shock standpoint. Generators as low as 15. So we're still, 8Gs, we're half what a generator should be able to withstand. So, that's doable, I think. Now, mind you, we have this huge cargo bay that's empty. And it's so empty that our total weight is probably a whole lot less than what
It's never going to be empty.
would be in there. Yeah,
It's
correct.
never going to be empty.
It's going to be much fuller. So we probably would have more mass. And now there's a couple of other things here. Say, for example, if the airbag didn't just, in our case, the airbag's a hard metal item, and it just goes smack and stops. Right? There's no deformation of the airbag. So if the airbag were to absorb the energy and slowly deflate, say perhaps over the period of 1 second instead of a tenth of a second, not surprisingly, we get 0.8 Gs. So what that means is that we could very easily handle a lot more mass if we have sort of the collapsible airbag.
Better bags.
Bigger airbags that collapse at a particular rate and allow us to reduce this speed. So if we doubled our mass, maybe our start speed would double. Maybe we would end up hitting the ground at twice the speed if we doubled our mass. We probably wouldn't be quite that linear. But in any case, then we could, again, really the more important item is to be able to decelerate in the airbag, with the airbag. Because then, 1.6 Gs, that's not much worse than you jumping off a step stool. So, that would be human rated, I guess I should say. So now that's with relatively low mass. And so I thought, okay, well, those are some good references. But what would be another good reference for what would be a G-force requirement? And I came across this Mars lander student tutorial kind of a thing. And let's see, I think I'll have to turn the system on there. So this is a student project, if you will. It's the old egg drop test, except it's all based off of the Skycrane lunar land or Mars lander.
Cool.
So far, it looks a lot like any other Mars landing.
So this is the one that came after MER, that used the airbags.
Yep. This is the one I'm talking about.
Well, this is the after
like
airbag.
Guy.
Yeah.
Oh, that's the. Yeah.
So we'd have this lander.
For the last 2 kilometers, look at the ground with the radar, and then about 20 meters from the surface, we
again 20-ish meters.
Which is called the Skycrane.
20 meters.
60 feet.
That guy.
And then he just drops it. Now, what's really interesting about this is the reasons why, and that's coming up next.
No dust.
Get rid of the dust issue.
Cut the rover free and fly off.
And then it just crashes into the dirt somewhere, I guess.
Else.
It doesn't try and actually. Oh, there it goes. Ploop.
It is a new architecture, and frankly, it looks crazy.
It did look crazy.
It looked scary. Very crazy, wacky thing. And it looked like that to the folks at NASA headquarters.
I wish I could fast forward.
It ended up being close to 2 hours. There's lots of questions, there's probing.
They ask about the airbags that worked so well last time.
Yeah. Do you hear the airbag commentary?
No.
Is 5 times heavier.
So the reason they couldn't use the airbags is because the rover's a lot heavier. And you would have had something like this. So, noopsie.
Oh, bummer.
And then the legged lander, 3-point.
Especially if it happened to land on a slope.
Bunk. so glad NASA produced the kind of crash films that I happen to do.
The sky crane, though, can drop the rover anywhere it can drive.
Utilizes the rover's inherent terrain hugging.
Well, that's interesting.
So that was his last comment, was that it utilized the rover's terrain hugging capability to land, and then anywhere the rover could rove, it could land. And that is the same kind of idea. The airbags could deform and allow, to roll over a rock and so forth, instead of having only 3 points, and those 3 points being, set crooked or sideways or what have you. And what it really comes down to is these rocket engines that they have here on the sky crane. They're fixed directionally, and they're just sort of splayed out to fire
but they
outward.
Could be not.
Well, you'd
so
have
you
to
could actually land that and it have actual real something on it.
Well, they thought about that, of it being of the rover being underneath or on top of it, and it landing and then rolling off. The problem was the instability of hills, and they don't have, as far as I can tell, these motors were not gimbaled motors like we have in the game.
Yeah.
So you couldn't do any kind of fine grain control.
What
with
year was this?
This was the latest rover, so this was actually a few years back.
That's what I'm thinking. I think they might have made some strides towards.
Yeah, and smaller gimbaled rocket engines. There's new rocket engines coming up all the time.
Yes.
So it might be more doable now. So here they talk about the G on the Mars is only 3.8, whereas it's 9.8 on Earth, but it's 1.6 on the Moon, so it's even less. So this gets into the various parameters of your design challenge to save the egg from dropping. They include the cost of materials in your budget as well. But, if you get a C grade if you manage this, a B grade if you can stay in the landing area and not kill your egg, and an A grade if you stay within all the size, cost, and mass limitations and so forth. And it's a 14-meter drop on Mars, which part of the task here is to recalculate how high that would be on Earth. So if you drop something from 14 meters on Mars with a gravity of 3.8, it should be going at a certain meters per second when it hits the surface. If you want to simulate that on Earth, you just drop it at a lower height, so that the speed at which it hits the ground is the same as though it were 14 meters on Mars. Maybe it's 10 meters on Earth. Anyway, that's part of the task, and is doing that calculation. And then also calculating, based off the mass, how much impact force you have. And in the end, get down here. Oh, it's around here somewhere. Where'd he go? There we go. Total max 10 Gs. So for the humans, they have a 10 G limit. So far, we haven't really blown our G limit, even with just the airbags. But we're going to see if we can do a little better with the retrofire. Let's get back over to the retrofire. Alright. Now, I'm undoing all these flights because if I leave them there, they all start creating new logs. And it's just not very useful.
No, I want to see the real data.
We'll clear the data view for now. Load up our other guy with thrusters. There he is with his little quad thrusters. Now you'll note this is about 2,500 kilograms, or roughly 5,000-ish pounds more heavy.
Wow.
And heavier. And that's because we have fuel in each one of these tanks. And we've got a lot more tanks. You're welcome. And because of that, all of our takeoff, we're going to need more main fuel in order to get to the same altitude. Everything, right? Everything.
More.
And plus, these guys provide nothing to the lift thrust. It's only for the landing. So otherwise, they're just dead weight until we're about to land.
And they're in the way. They make it less aerodynamic.
Luckily, I'm adjusting. It's an imagine thing right now. But
Imagine thing.
If you remember the picture of the of the this is the Centaur upper stage, and it was sitting inside a big fairing.
Yeah.
And so the fairing would cover all these in theory.
Yes.
But very quickly it looks like it is true that the Centaur upper stage is becoming the shipping container of space. What can we do with all these leftover center stages or upper stages? I don't know if there's all that many left over really, but so you'll note that the engines are not out on the outer edges, correct? They're not. This one isn't way up here on the edge, and I did that to begin with, not really thinking much about it, but this upper part here, this cargo bay is empty. So it's fairly light compared to this fuel tank down here. Now, in the old days, you would have had to calculate all this kind of stuff and figure out where exactly the middle of it is, but here you can just say, show me the center of mass. So, right now, while it's landed, this is the center of mass, where all the fuel is in.
Fuel, yeah.
With fuel.
Is it fueled?
With fuel, yeah. So, you'll note that the distance from this nozzle to the center line and this nozzle to the center line are pretty close, but this is slightly further away, and that's because this center of mass changes as the tanks drain, it goes up. So, for example, if I go in here to the tank and I lower the fuel, see how the center of mass goes up?
Yes.
So by the time I'm hovering, or about to hover, I need to adjust that.
Yes.
So all of this is the reasons why they're in the position they're at, so that they're actually stably over the center of the center of mass.
What is the Tinker panel? Excuse me.
It just has all sorts of little things that you can play with. You can make things, you can fiddle with the mass, make it heavier or less heavy, you know.
It's not like Tinker Air Force Base?
No, not Tinker.
Okay. I thought it was like something special that only they knew.
Well, it is, you know, you can disable the Tinker panel so that the calculations go faster. And like they said, these are various use at your own risk properties that haven't been fully tested.
I see that now.
But you can change how much of a heat shield it provides and how much drag it provides, things like this. What's its max temperature that it can withstand. So there's any number of things you can change. I haven't gotten too far into it, except for some smaller bits. I've shrunken the command pod. Yeah. I've shrunken the command pod down inside here. Since really it should be just the command chip, but that was all trying to figure out the logging. Alright, so we've already got them ready to go. I guess we should give you a quick look at the code for this, since it is slightly different than what we were doing last time. So I created this hop and hover function, which basically allowed me to jump up to a particular altitude and hover there on all four engines, so that I could see how well it hovered. Now initially I didn't have the engines balanced, so it was spinning around in circles really fast. I was like, I should really take the aerodynamics and the center of mass into account here. So essentially what this does is, instead of coming down to a pad printing height, it comes down to a height where we can stabilize the lateral speed, and then the final stage it kicks over, disables the rear engine, enables the four quad lander engines, and then it attempts to just descend to 0 meters above ground. Unfortunately, it rolls, or can roll, and that will, since there's 4 jets, that, well, you'll see it here shortly. Unfortunately, I still have to pilot the roll because there's no way to fix the roll at 0 programmatically. It is a request, it's already in place. I've upvoted it. So, let's just save our craft with our thrusters, head on out. Come back over here and get our new data going. Alrighty. There's our data view. And you can see we're wobbling. Stabilize. Set the mode to ground level. 5,000 foot target. Heading due west. Makes it easy to remember too. And then tilting over to 45 degrees. And take off. There we go. Back over into this little test realm. Which we got rid of our previous craft over there anyway, so.
Good. Everything looked good.
We'll do the nice 2-speed. Move things along a little bit without, we're getting a drop in, we're getting a seriously dropped frame rate, unfortunately. Sorry for the glitchiness, but views, this data viewer is all written in Python.
I don't really see it glitchy.
It's dropping the frame rate a good bit. But we'll be landing shortly. Be sure to put your tray tables and seat backs in their full upright and locked position as we come past our apoapsis. Kick back into retrograde, and you'll note we're landing at 1,000 AGL instead of 600. Again, we've got all this extra mass, so it takes us longer to slow down. Since I have matched the power of this engine to that of the Centaur, the real Centaur, and at least the dimensions of the upper stage. I don't think I have the mass of the upper stage completely accurate. It won't matter because it's going to depend on what you put in it. Right? You're going to put different things in this this stage.
Everybody's going to put different stuff.
Yeah, so it's going to right. It's going to depend on what the project is, I guess I should say.
Well, every project is different. Every project's going to have something different.
Right, and then it may also be that you have stuff that once you land, you want it to get off of the lander.
And do
maybe
something else.
Rove around, perhaps. Let's see, where do we want to land? You seem to be doing. You seem to be going in a decent direction. Maybe we go that way a little bit.
It's a lot of chatter on the thrust.
Again, it's above ground level.
Yeah. And those are bumps and craters.
Sorry. So here I fixed it to sea level, which is really more of a fixed altitude relative to the center of the planet, I guess, is your number you're going to use here. Alright. Let's take her off at 2x speed since I'm not that fast a pilot. And we will back up, get our surface speed down. We got our lateral speed shown here on our bottom chart. Doesn't have a lot of detail, but zeros at the bottom. And since it's overall lateral speed, it doesn't matter which direction, it never goes negative. You'll see we've got it much smoother and a lot less fuel usage as well.
Yes.
There we go, that's roughly 0. Now it is time to drop down to our final decision altitude, if you will. This would be where we would start looking around and making sure we're where we want to land and ready to flop over. So that's what we do. We flop over and land. Looks like our vertical speed is not charted properly, but we'll get to that after we land. I need to, since I do have to fly here, I'll have to maintain a little bit more concentration on the craft. We get down to our 100 meter. 170, 60, 50. And we still got a little bit more, a little bit lateral speed. You can see it picked up here. Alright. So again, we can force this back to above sea level mode. And then I can Back it off to slow it down. I said this was the last time I was going to do this, but since this is a test about landing and not how well you can control the direction you're going. Come on now, slow down. Yeah, 2, 1, watching the chart. There we go. Alright, so now it's all going to happen really quickly. Let's not do what I've been doing for like the 7th or 8th time, which is forget the landing gear. So here's our landing gear airbags. We've inflated them. It's going to get all sorts of dramatical right here, right now. Flop! And this is where I can't control the rolls, so I got to be real gentle with it. This is all using the same logic as vertical flight.
It looks like Thomas the Train.
Is he? Thomas the Space Engine. So now we're picking up some lateral speed because, unfortunately, again...
Oh, that can be good.
It's okay. Woo, woo, woo. Woo, woo. Plop. There we go. Nice, soft, gentle landing on the airbags.
Oh, that's pretty good, huh?
So it actually turns out it doesn't matter whether you're using retro or just the flop over technique. Either way, airbags seem to be a decent way of having
I like it.
Adjustable
I like
landing,
it a lot.
self-adjusting landing gear. Let's get back over to our chart here, and we'll have to
Will everything
fix
survive
up
is the
chart
question,
3.
right?
Yep. So let's see, we need to get this back to auto. So there's our super noisy vertical speed. It only looks noisy because we're not getting the full view of it. I don't know that there should be some way to set those back to normal. So you see this was our launch, the descent, our hovering above ground, hovering above at a fixed altitude. Here's our final descent stage, again hovering above ground and hovering above a fixed altitude. And then if we zoom in just on this, you can see we got actually all of this instability. This is when we first kicked over. Then we stabilized and we got back up to 0. And so this little tiny bit down here was our final landing force, which was somewhere sub 1 meter per second. So we got maybe 0.9 meters per second was the last one before we finally hit. Worst case scenario, it was 1. So again, looking back at our system view and our calculator, if we managed to have -1 over 1 second with the airbags deflating, 1/10 of a G. That's like the nice, softest landing I could think of. So it's a trade-off. You get all that extra weight for retro rockets, but you get a super, super soft landing. Or bigger airbags. And again, when we get to when our cargo bay is not completely full of or isn't completely empty, then we'll probably have to reset our engine placement. I just got to turn off the orange black box, so that'll stop the logging. so I can leave this craft here and it won't come back to turning back on the log. So, one more try on this, one last try with the thrusters, which is we're going to replace this cargo bay with a big hunk of fuel tank, except it's going to be containing water. So now the mission, if you will be to collect water from one part of Luna, fly off to another part of Luna, land softly enough, and of course if it's water, it can handle some G-forces, so we'll probably not have to need these retros, and we can land with just the airbags, but then we'll get an idea of what it would be like to land only with airbags, but with a much more significant mass. And of course the rockets should be more balanced by then. It actually kind of reminds me of Battlestar Galactica when you do this and you take in the airbags. That one kind of looks like it. So we'll put his airbags back out so he has a nice soft place to sit. Is Thomas the space plane?
I like it.
Alrighty, well that was pretty much what we had for you today. Be sure to like and subscribe and follow us and ring the bell so you get notifications. We're kind of got a mixed up schedule now since things are kind of up in the air. And hopefully they'll be up in space soon. So we'll see you next time.
Thanks. Everybody. Bye-bye.
Yay!